YouTube as usual. Okay. So before we start, let me give you some announcements. I'm grading the exercises for Unit 2. I'm like halfway my way through, and I expect to have them ready for Monday. Okay, so at the most on Monday you can expect to have the grades for the exercise of Unit 2. I will give you the grade through the task and some comments on the things that may be wrong with your answers. Okay, and then you can email me or we can uh, connect by Microsoft Teams or Skype or whatever for me to explain any question that you may have on the grading. Okay. For Monday, I will prepare a video lecture, and that is going to be the last video lecture of the course of this unit and and of the course. And then on Wednesday, we are going to have again a live session like this one with more exercises. Okay. On Friday. Friday it's a holiday, so there will be no lectures. And then on Monday we have the last lecture, which will be again live. Okay, for you to ask. Well, we will have two live sessions because there are two groups for Monday. Okay, so we will have two different um, live sessions, one at 11, the other one at 12, and you will be able to ask any question about this unit or any of the topics that we have covered, about grading, about the exam or whatever. Okay, and I will, if we have free time, I will solve more exercises. Okay, so that's the plan for the rest of the course. And the last announcement is that, as I have already mentioned in the video lectures, from the school, from the head of the school, they have asked you to remind you. They have asked me to remind you that, if possible, you should fill in the academical survey with the questions about the course and all that. Okay, so if you can, please spare a few minutes. Go to the virtual campus when you have some minutes free and fill in the survey. Okay. Any question about that? About the planning or uh, any other thing? I have. I have. I'm missing again the chat. Okay, no questions. Okay, so I'm going to solve some of the exercises on the worksheet that I have uploaded to the virtual campus, and I'm going to focus especially on exercises about Hamiltonian paths, Eulerian paths, and all that. Okay. And in the next live session on Wednesday, I will cover different kinds of exercises. But since in the video lectures I had no time to solve many of these exercises, I want to do it now. Okay. But if you have any question or if you want me to do a different exercise that you have tried and have questions about, please tell me. Okay, so I'm going to start with exercise 9, which is directly about finding Eulerian paths on or cycles on graphs. Okay, so what we need to do here is to check whether such a path or cycle exists. And if there is such a path, then we have to apply the algorithm in order to find it. So let me copy the first graph. I'm copying it now on my whiteboard. Then I will switch with the tablet. And then I'm going to switch to that screen, that window, and okay, I have it here, and now I can solve it here. So we need to check whether this graph has a Eulerian path or a Eulerian cycle. Okay, and you know that in order to do that, we need to compute the degrees of all the vertices. Okay, so this vertex has degree 5. This other vertex has also degree 5. 5, 5, and 4. Okay? This is consistent with the results that we have studied because the number of vertices with odd degree should be an even number. So here we have 4 odd vertices, 4 vertices with odd degree. Okay? And the results about the existence of Eulerian paths tells us that for such a path to exist, the number of vertices with odd degree should be at most 2. Okay? So in this case, we do not have any Eulerian path. Okay? So this is quite easy to solve. We just compute the degrees and we count the number of odd vertices, and if it is bigger than 2, then there is no Eulerian path. Okay, any question about this exercise or this part of the exercise? Let me, I need to go. Okay, no questions on the chat. You can also turn on your mic and tell me if you have any question. Okay, but I will be checking the chat eventually. Okay, so second graph. Let me copy this graph here on the whiteboard, and then I will switch again the screen, the window. Okay. I think I have it now. Let me add the numbers. Okay. Okay. So I'm going to the. Oh, this should be. It's not very clear. So this should be 5. Okay. So here we again need to compute the degrees. Okay. So this vertex has degree 5. This vertex also has degree 5. This one has degree 4. This one has degree 4. And this one has degree 4. Okay? In fact, we have removed, there was this edge here that is not in this graph anymore from the previous graph. We have removed that edge, and then we have decreased the degree of these 2 vertices. Okay, so now we have 2 odd vertices. Okay, we have 2 odd vertices, and this means that there is an Eulerian path in this graph, not a cycle, but an open Eulerian path. And we also know that it should start either here and end here, or the other way around. It should start in one of the vertices with odd degree, and it should end in the other vertex with odd degree. Okay? So let me erase this and try to apply the algorithm in order to find the path that uses all the edges once and only once. Okay? And for that, you know that we need to add a fake edge between the 2 vertices with odd degree, because with this edge we now increase the degree of this vertex to 6 and of this vertex to 6, and now all the vertices have even degree, and then we know that there is an Eulerian cycle in this graph, and we can apply the general method, and then we remove the fake edge, and then we obtain the Eulerian cycle, the Eulerian path from the Eulerian cycle. Okay, so we need to add that fake edge, and I'm going to give names to the different edges, because we have edges that connect twice several pairs of vertices, because for instance we have two edges between 1 and 2, and then I cannot identify an edge with just the extreme vertices. If I say the edge from 1 to 2, we don't know which one it is because there are two. Okay, so I need to give names to these edges to have them straight, to know which one we are referring to. So let's say that I call these edges like this, J, K, and this last one is L, for instance. Okay? And now, remember that the algorithm tells me that I need to select an initial vertex. I can choose any of the vertices in the graph, and then I have to construct a cycle that starts and ends in that vertex. Okay, so I'm going to select, for instance, 1. Okay, and I select one of the edges that goes out from 1. For instance, A. Okay, you can choose any of the edges. And then I need to select another edge from the new vertex in order to get back to 1. Okay, I can do it in the way that I like the most, and eventually I will return to 1, because since the degree of each vertex is even, when I enter the vertex, I always have another edge to go out from the vertex. Okay, and then since the number of edges is finite, I will return to the initial vertex somehow. Okay, so for instance, I'm going to go now with J to 5, then I will go to 4 with this edge here, then I'm going to go to 3, and from 3 I'm going to go directly to 1. Okay, so I have computed the initial cycle. Okay, and I need to check if I have used all the edges in the cycle. Well, obviously I have not used them. Okay, I have not used all the edges, so I need to repeat the process, but now without these edges that I have already used. So I'm going to write here the cycle that I have selected, because this is like the supporting cycle. I will connect all the other cycles that I'm going to generate to this initial cycle. Okay, and I need to remove the edges that I have already used from the graph. Okay, so I'm going to mark with yellow those edges that I have already used. Okay, and I cannot select them anymore. Okay, any question up to this point? Let me check the... Okay, no questions. Okay, so now I'm going to erase this, because I need to apply a similar technique once again. Okay, I need to check, I would need to check whether the graph is still connected. Okay, But in this case, it is clearly still connected because I can go from 1 to 2 with B, then with I to 4, or let me, yes, to 4, and then to 5 with K. Yeah, the graph is still connected. Okay, so I'm going to select a different vertex now, or I can select the same one. For instance, I will start with, with 3, and I select another cycle. Okay, so now, for instance, I go with E to 5, and then I only have one edge remaining. Okay, I'm going to go marking the edges that I'm using to know what it's available and what is not. So now I need to use K, okay, to go to 1. Let me mark K, and then I can use, for instance, D. Oh, sorry, the other, the other, the other tool. So I use D. Okay, so let me mark that I have used here D, K, and E. Okay, so I write here the edges that I have used. This is the second cycle. Okay, now I only have a few edges remaining. Okay, for instance, there are no edges for 3 or 5. 3 or 5 have all their edges already used up. So I have one that goes with L to 2, with B also to 2, and then I have here H, I, and 4. This is what is remaining now. Okay, and here, well, of course I can select, for instance, 4 and go to 2 and back, or any other cycle here with just 2 edges. But well, it's clear that I can, in this case, I can obtain a complete cycle with all the edges here. So for instance, I can go something like L, then H, then I return to 2 with I, and then I use B. Okay? Yes? You see the idea? So now I have used all the edges. All the edges are used, but they are in cycles that are separated from each other. Okay, they are not in the same cycle. I need a cycle with all the edges together. So in order to do that, I need to compose these cycles, to join these cycles from the bottom up. Okay, I have made a recursive application of the algorithm. In this case, since all the graphs that I had at any given moment were connected, I had no more than one recursive call. But if we have several different connected components at one moment, then we apply the algorithm in each of the connected components. Okay, so we may have several parts of the graph, and we work in any of the part in all the parts of the graph, and then we go back and we join the different cycles. Okay, but in this case, from here we made this call, and then we made this call. Okay, so in order to reconstruct the whole cycle, we need to go in the other direction. Okay, we need to come back from the recursive calls and try to join the cycles together. Okay, so first I need to join these two cycles here. Okay, and in order to do that, I need to find a vertex, at least one vertex that is common to both cycles. So let me write here the cycles. This is the first cycle, and then I'm going to do it in a different color, for instance, red. The other cycle. So the other cycle is L here to 2, then H to 4, then I to 2, and then B back to 1. Okay, so in this case it's very clear. It's very clear that they join here. Okay, but we may have several different vertices where we can join the cycles. Okay, in that case we select any of them, but here we can just join the cycles at vertex 1. Okay, so we start with one of the cycles, and when we reach the vertex in which we are going to join the cycles, we insert the other cycle. Okay, so here I, for instance, start with this cycle with EKD, and I start in E, then I use K, and in this moment I have reached 1. This is the point where I'm merging the two cycles, where I'm joining the two cycles. So here I insert the second cycle, okay? Because I know that the second cycle will start in 1 and will end in 1, okay? And then I can include the final edge from this cycle to close up the whole cycle. So let me draw it or write it in red again. I will have here L, H, I, and V. Okay, and I'm back in 1. That's why I can join the two cycles, because the cycles make a detour. They go to other vertices, but they come back, and then I can add the rest of the edges in this cycle. Okay, so the final cycle is going to, the final edge is going to be D. Okay, is this clear? Any question about this? Okay, thanks. So let me eliminate this, and then these two cycles here are already joined. Okay, these two cycles here are already joined. So I need to join this overall cycle, or the merging of the two cycles with this one here, which was the initial, and then we are done. Well, almost done, because we have to eliminate the edge L. But we will have the overall cycle, the complete cycle. Okay, so again we need to select a point in which they join. But since this initial cycle uses all the vertices, then I can select any of those, and this one also uses all the vertices. I can select any of the vertices as an initial or as a merging point. Okay, if there are more than one vertex in common, I can select any of them. Okay, so I will select, for instance, the starting point of this cycle, because then it's just merging both is just writing one and then the other. Okay, if I select this vertex to join, since this initial cycle starts and ends in that point, then I can just put the second cycle after it. Okay, so I start with A, J, G, F, C, and then I can write this cycle. Okay, but I need to write that cycle starting in vertex 1, because here I'm now in vertex 1. Okay? And then I need to see in this cycle here where is the point that in which I reach vertex 1. So I here start, if you see, I start here in vertex 3. Then I move to vertex 5. Okay? And then here, just before using this L, I am in vertex 1. So that is exactly what I need in order to join the edge here. Yes? This is a bit more subtle, but I think it's not difficult. Okay? So here I start to join from this edge, which is the one that goes out from 1, which is the vertex that I'm in after I have used edge C. So here I add L, H, I, B, D, and now I need to go back to the beginning because this is a cycle. When I use D, I return to 3 because this is a cycle, this is closed, and then I can use E and K. Yes? You see the idea here? Let me clean up all this mess a little bit because I need some more space here. And let's first check that this is in fact an Eulerian cycle in the graph. So I'm going, well, I need to use more colors. So I'm going to use what color? Why can't I select? Ah, yeah, okay. So for instance, green. Okay, so I'm going to mark the edges that I'm using in this cycle, in this complete cycle. So A, then J, then G, then F, then C, then L, then H, then I, then B, D, E, and finally K, and I return to 1. So I have used all the edges in the graph, and I have returned to the initial vertex. Okay, so this is indeed an Eulerian cycle. But I'm not done. I'm not done because I need to remove the edge that I have included, the fake edge that I have included in order to be able to construct the complete cycle. Okay, so what I'm going to do is to split the cycle here, removing this edge. Okay, and then I will obtain the Eulerian path that is open and starts in either 1 and ends in 2, or starts in 2 and ends in 1, because I'm removing exactly an edge that goes from 1 to 2. Okay, and I can do it either starting here and moving to the right, or starting here and moving to the left, and taking into account that this is a cycle. So after A I can take K, or after K I can take A. So let me go from left to right, for instance, and then I write H I B D E K. After K I have come to 1. So I can use now A to go to 2, and then J, G, F, and C. And as you can see, in this case, I have started in 2 and I have ended in 1. If you take it in the other direction, starting with C and going to the left, then you will start in 1 and you will end in 2. Okay? So in fact, it's the same path, but traversed in the other direction. Okay? You see the idea? Any question about this exercise? It can be a bit long, but it's not complicated. The only point in which you have to be a bit careful is when you join the different cycles. Okay? But if you do it with this technique and in order, you will have no problem. Any question about this exercise? Okay, cool. So the other exercise or the other graph here is similar because, well, this edge, this vertex, this initial vertex here, well, it doesn't allow me to select it. With this initial, the first vertex here is of degree 1, the last vertex is of degree 1, and the other vertices have degree 4. So again, we have an Eulerian path that is not closed. And you need to add a fake edge between the first vertex and the last one, and then you do something similar to what we have just already computed, and you obtain the path. Okay, so I will leave to you to complete that graph because it's exactly the same. What I want to do now then is to focus on exercise 10 because it's also related to this algorithm and this concept of Eulerian cycles, but it's a bit different, and it's also related to the kind of exercise that we are going to ask you to solve for the evaluation of Unit 3. Okay, I will explain that in more detail in future lectures. Next week, I expect to upload all the details about the exercise. But the idea is that you need to invent a problem that it's not related to graphs. Okay, in the statement of the problem, you cannot use the word graph or the word vertex or the word edge or the word path or the word Eulerian cycle or any of that kind of things. But the exercise has to be or should be modeled with a graph and solved with a graph. So this is an example of this situation. In this problem, we are given a map of or the drawing of the different rooms in a house. Okay, and the broken lines here indicate doors. So, for instance, we have a door here between room 1 and room 2, another door here between room 1 and room 4, another door here between 1 and the exterior of the house, okay, and so on. So here we do not mention vertices or graphs or paths or any of that thing, okay? And the question is if it is possible to use all the doors once and only once, okay? And it's stated that we can go out of the house, of course, because we need to use, for instance, this door or these two doors that go out, okay? So as you can see, there is no direct reference to graphs here. They don't know about graphs. Can you find a way of using all these doors once and only once? This is a question that you can ask anybody, even if they didn't take the discrete mathematics course. But this question can be solved with graph theory. Okay, so this is what we will be expecting of you, to invent a problem that you can state and tell anybody to solve, but then the easiest way to solve it is with graph theory. Okay, so here what is the way of solving this problem? Well, when we need to model something um, with a graph, of course, we need to identify vertices and edges. Okay, it seems clear. It seems clear that we are going to need the concept of Eulerian path because we are going to use doors once and only once, and it either has to do with Eulerian paths or with Hamiltonian paths, okay, depending on whether the doors are vertices or the words are the doors are vertices or the doors are edges, okay. This is something that in most problems you have to decide what you use as vertices, what you use as edges, and it can make a difference, okay. So we need to model this, and we need to select what are the vertices and what are the edges. So here, the easiest way, and it seems pretty obvious because it's similar to the problem with the Königsberg bridges, what we can do is to select the rooms as vertices. Okay, I'm drawing the vertices now on the whiteboard. I will show you in a minute. And then the doors clearly connect the different vertices. Okay, so I'm drawing the doors that exist between the different rooms. Okay, let me go there, and we have here this. But then we have the doors that connect the rooms to the exterior, okay, to the outside of the house. And it's not so clear how to use those edges, because a naive solution would be, for instance, to say that 1 is connected to 4 because I can use this door and then go inside again through this door. But 1 is also connected to 6, and it's 2 times twice connected to 3. Okay, and so I could try to use doors that go out and go in as edges. So this would be one edge, this would be another edge, and so on. If you do that, maybe you can solve the problem. Because, well, just by trying different possibilities, maybe you can solve the problem. But it's complicated, okay? So the trick here is to include a new vertex that is not apparent in the statement of the problem for the outside of the house, okay? So if I add another vertex, 7, for the outside of the house, then it is clear that all the doors that connect a room with the outside will connect the corresponding vertex with the new vertex, with 7. Okay, so I'm drawing that now in my whiteboard. I will show you in a minute. Okay, and with that, it will go like this. With that, 7 is the let me move this to this. Okay, so with this 7 is the new vertex, and then each door is an edge. The problem with the other representation, where for instance you use a door to go from 1 to 3 or from 1 to 4 because they both have doors to the outside, is that then it is difficult to keep track of which doors have been used and which doors have not been used yet. But here each edge is exactly one door. And then the problem is transformed into the question of whether this graph has an Eulerian cycle or an Eulerian path or not. And that is something that we know how to solve very easily. Okay? I'm not so interested in the solution to the problem, on whether there is such a path or not, but I'm very, very interested in your understanding the way in which we model the problem with graphs in order to be able to solve it with the algorithms that we know. Okay, is that clear? Yes, yes, thank you. Okay, so now we can trivially solve the problem because here we can compute the degrees of the vertices in the graph, and we have 2 3s here, now 4 2 1. Okay, I have found 3 vertices with odd degree. There will be at least another one because the number of vertices with odd degree is always even. But since I have found 3, I know that there is no Eulerian path in this graph. Okay, let me complete the computation. 2 and this is 5. So there is no such a way. There is no way of using all the doors once and only once. Okay, and this was easily solved because we transformed the problem into an adequate graph. It is very important not only to use graphs, but to use the adequate graph. If you use a different graph, maybe you can solve the problem, but it's not so easy because then, for instance, you don't keep track of the doors if they are used more than once or something like that. Okay? You understand the solution to this problem? Yes? Okay, so there is another one which is very similar, which is number 14. You can try it on your own. If you find any problem with it, just email me or leave a comment in the discussion forum. But I want to move to number 11. We have a few minutes left. Let me tell you a bit about 11, because this one is similar, but it's there is a detail that sometimes makes it a bit more difficult. Okay, here we have a mechanotoy. So these are like construction pieces for children, in which you can connect some pieces with others. Okay. They have connections, and not all connections are the same, so some pieces connect to others, but not to all. And here we have 5 types of connections. Okay, so those connections that have the same number can connect to each other, and the others are not compatible. Okay, and we have these pieces from A to G, and they all have 2 connections. For instance, piece A has connection type 5 and connection type 1. And the question is whether we can make a unique figure with all the pieces, connecting all the pieces together. Okay, so we need to connect, of course, those pieces that share the same connection. Okay, so again, we have this idea of using, and the pieces, of course, can be used only once because we only have one piece of each kind. So again, we have this question of whether we can use something once and only once. So the immediate idea is to try to transform this into a graph and see if we can use what we know about Hamiltonian cycles or Eulerian cycles and paths, and see if we can solve the problem. Okay. The trick here is that now maybe it's not so easy to notice what should be vertices and what should be edges. Okay, so in my experience with this problem, the first idea that everybody has, or almost everybody, is to use the pieces as vertices. And then, for instance, if A is a vertex, then we say, well, A has connections 5 and 1, so I draw an edge from A, for instance, to B, because Well, they share a connection of type 1. Okay, so they can be connected, so I draw an edge there. And I also connect A to F and to G and also to E because they share connection 5 and so on. Okay, so you have these 7 vertices, pieces from A to G, and those edges. Well, if you try to do that, maybe you can solve the problem, okay, by trying different possibilities, but it's very complicated, okay? So the not so obvious choice here is to use the pieces as edges and the connection types as vertices. In that case, if you use that representation with the graph, then the problem becomes much easier, because now uh, each piece is uh, naturally an edge because it has two numbers. Okay, so A connects vertex 5 with vertex 1, and that is an edge. It's a connection between two elements in the graph. Piece F, for instance, connects 1 to 2. Okay? And then, if you try to find an Eulerian path or cycle in the graph, the edges are the pieces. So you are going to be using each piece once and only once. Okay? I leave to you to try to solve the problem. Okay? Because once that you know that the pieces are the edges, the problem is easy. It's just to draw the graph and make the computation of the degrees, and you can solve the problem. The trickiest part here is to notice that you should use the edges, the pieces as edges. Okay, there is of course no recipe for this kind of problem that always works. But as a general rule, if you have something that is described as two numbers, well, that has that smells like an edge. It seems possible at least to try to represent that as an edge, and then the numbers as vertices. Even if it is not it seems that it makes no sense, because what kind of vertex is a connection type? Well, doesn't seem to be something natural or an easy choice to make. But the general rule is that, well, if you have something that is described as a pair of elements, it is possible that it is a good choice for an edge. Okay? Do you understand how to represent the graph in this situation, and then to solve the problem with what we know about Eulerian cycles and paths? Any problem with this? So please try to complete uh, this graph here that we have not solved, and the solution to this exercise. There is another one. I think it's number 6. Number 6 is similar to this one, okay? But this is about domino pieces. But it's the same. Again, you have here pairs of numbers. The pieces are pairs of numbers, so they should be edges. Okay? So try please and solve those exercises. If you have any problem, if you find any difficulty with it, email me. And let me remind you that I will upload a new video lecture for Monday. I will upload this recording also to YouTube. I will try to do it this very morning. And then on Wednesday we will have another live session. I will create the appointment in Microsoft Teams, and then on Friday we have a holiday, and the next Monday, the first Monday of May, we have the final lecture again live through Microsoft Teams. Okay? Any question? Any comment? Okay, so thank you very much for your attention, and please feel free to email me with any question that you may have. Okay, so I'll upload the video for Monday, and we will meet again on Wednesday. Bye, and have a nice weekend, and thank you for your attention. Bye, bye everybody.